In 1959, Giuseppe Cocconi and Philip Morrison wrote their seminal paper, Searching for Interstellar Communications, that set off the search for extraterrestrial intelligence. Over half a century later, we're still looking. And other than a few unverifiable signals that may or may not have been of alien origin, the search continues, but without much success. But within this is an often ignored aspect. Do we really know how to look for alien technosignatures? This has shifted across the history of SETI. In Cocconi and Morrison's day, the idea was to look for a beacon, an intentional blaring signal from somewhere in the galaxy that announced to all of us that might be out there that we are not alone. Today the approach is more nuanced, with targeted searches hoping to eavesdrop on someone's probably very faint internal communications. But we can only go so far with that. We point our radio telescopes and monitor individual star systems for a short time, and if we see nothing, we move on to the next target. But there are other ways to do SETI, such as all-sky surveys, but also the search for very short-term transient phenomena that haven't really been looked for before. As things are now, we are missing those kinds of signals, should they be there. My guest today's research involves searching for just such phenomena, and also working with the world's largest radio telescope, FAST, in hopes of someday spotting an alien civilization through different thinking. It may well be that we've been missing the others all along.
You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dan Werthimer. Dan Werthimer is the co-founder and chief scientist of the SETI Home Project at the University of California, Berkeley. He specializes in signal processing for radio astronomy. He has been doing SETI since 1979, and he runs the SERENDIP, Optical SETI, and CASPER projects. Remember to subscribe to Event Horizon so you never miss an episode.
Dr. Dan Werthimer, welcome back to the program.
Glad to be with you, John.
Now, Doctor, we have a developing situation with SETI because the FAST radio telescope in China is online. And with the loss of Arecibo, it's really the only telescope of its class. And the idea is to use it in part for SETI. And you're involved with that. Tell us everything about FAST and what makes that telescope special for SETI.
So FAST is, as you mentioned, it's the world's largest telescope. So Arecibo, the one that collapsed in 2020, ran for about 60 years before it collapsed. That was 300 meters across. FAST is 500 meters across. The Arecibo telescope could hold about 10 billion bowls of cornflakes. So this one can hold about maybe 25 billion bowls of cornflakes. So it is the best telescope by far on our planet for looking for ET and finding out if we're alone. Is anybody out there? So FAST is a pretty new telescope. I think it's maybe 5 or 6 years old. And this already doing spectacular science. There's several SETI searches, but the big science that's come out of it is pulsars and fast radio bursts and mapping the galaxy, learning about other galaxies that are almost at the edge of the universe, where the light and radio comes from us travels billions of years before it gets to us. So we can learn about the early universe, and we've learned a lot about these things called fast radio bursts, and that allows us to measure the density of the universe. It allows us to weigh the universe, because as the signals come from the fast radio bursts and travel through the extragalactic medium, they get distorted, something called dispersion. And by measuring that, we know how much material is between us and this distant fast radio burst at the edge of the universe. So we can actually weigh the universe from fast radio bursts. Anyway, so it's already doing this great stuff, which I know you don't want to talk about today. You want to talk about SETI. And now it's doing some really interesting SETI.
Now, what sets it apart as a SETI experiment from one that's done with a steerable radio telescope?
So this telescope, the FAST telescope, is very much like Arecibo. In fact, it was kind of modeled after Arecibo. And as your question points out, it's not a fully steerable telescope. It's not one of these dishes that can point. It's built into the ground. It looks like a kind of big crater, but it can point. It turns out that the mirror that's built into the ground, it's made of actually thousands of little segments of individual mirrors. And those mirrors are on actuators, and they can kind of pivot around and they can move up and down. That's one way to point the telescope. And another way they can point the telescope, even though it's not fully steerable, is that the receiver, which is up at the focus way above, I think it's like 200 meters, 200 yards above the mirror, this dish that's sitting in this crater, that thing can also move around. And when you combine those things, the action of the mirror that's sitting a little bit above the ground and the action of being able to move the receiver that's suspended on cables above the dish, they are able to cover about half the sky. So the FAST telescope, even though it's not a fully steerable telescope, can see half of the universe.
Now, how did the SETI program with FAST get started?
Well, I'd like to say that I had a lot to do with that. So I've been working with China since the 70s. I was one of the first Americans to go to China in the late 70s, and I taught there for a year. And I met a lot of really interesting astronomers and young students that were excited about astronomy and SETI. And I sort of got them interested in SETI, but they didn't actually do any SETI until they had this big telescope. But I've been working with China now for, I guess, 45 years. I've had a lot of students come from China every year, and they spend a year with me, and they learn how to do SETI and how to do other kinds of radio astronomy. And so we've been engaged with our Chinese colleagues for a long time. And I was one of the people that helped them design some of the stuff for the FAST telescope. My group is really good at building kind of digital instrumentation. After you receive the signals with a receiver, then you have to analyze them in real time because it's very high speed data. Anyway, we helped them build the instruments. They have super sharp people, so they did most of the work, but I sort of kibitzed on that. Anyway, so I was involved in the design of the FAST telescope, and I sort of encouraged them to do SETI, and along with their other searches for fast radio bursts and pulsars and mapping our galaxy and so on. So I've been working with them ever since on these SETI programs at FAST.
Now, have there been, with that particular experiment, have there been any interesting candidates found yet?
No. So we're really just starting off. This is early days of SETI. There are two main programs. So one of the programs on FAST is a big sky survey. And what we're doing there together with our Chinese colleagues is we are raster scanning the sky, going back and forth and back and forth. And it takes 5 years to do a thorough survey. It's called the Craft Survey. And it turns out there are a lot of other people besides SETI people that want to survey the sky and just look at every star and every galaxy. So at the same time that we're doing our SETI experiment, there are other experiments looking for new pulsars, looking for fast radio bursts, mapping our galaxy, mapping other galaxy. There's a lot of things happening. Everybody wants to map the sky, or almost everybody. And so we're all kind of sharing the signals coming out of this telescope. And one of the experiments is this SETI experiment. So that's one of the things going on, just a big raster scan of the sky, every star and every galaxy that you can see from the FAST telescope. That's called the Sky Survey. Then there's another thing we're doing together with our Chinese colleagues, which is targeted SETI. And that's where you use dedicated telescope time and point the telescope at interesting objects. And you can look at maybe nearby stars that are known to have planets, and especially stars that have planets that are kind of in the Goldilocks zone, not too hot, not too cold, or planets that might have liquid water on them, or something where you think there might be life. There are other kinds of targeted work where we are looking at the very best signals from our 20-year SETI at Home survey at the Arecibo telescope. So we ran at Arecibo from 1999 through 2020 when the telescope collapsed, and we used 8 million volunteers to analyze the data from Arecibo. And we went through that data and we found the best candidate signals, maybe from ET, probably not, but we thought we've looked at about 100 of them using the FAST telescope, 100 different places in the sky that looked interesting to us. And we've been working with our colleagues to reobserve those places, and we're about to observe another 100 or so.
Now, interesting signals would basically be narrowband signals, right?
Right.
I mean, wouldn't that be the main hallmark, or is there some other type profile you might look for? So what was interesting about SETI at Home was that we had a lot of computing power. So we looked for a huge variety of signal types. So I think it was the biggest supercomputer on the planet, and we had it for many years, 24 hours a day. Nobody else has that kind of access to it.
It was composed of just small computers, but because there were millions of them, it was an incredibly powerful thing. So it made it extremely sensitive. It was the most sensitive search that's ever been done, the SETI at home search. But it also, back to your question, it looks for a very rich variety of signals. So it looked for those narrowband signals that you were asking about. It looked for all kinds of different bandwidths, so wideband signals, intermediate. It looked for 13 octaves of different bandwidths. It looked for a lot of pulsing signals. It looked for those kind of things. It looked for chirping signals that weren't staying at one frequency. So instead of going, staying at one frequency, it would go, or, and those kind of signals can happen because if they're transmitters on planets that are spinning around, like our Earth spins 24 hours a day, that introduces an acceleration with the transmitters moving around, and that introduces this thing called a Doppler shift, and the signals will appear to be changing in frequency. And we don't know the rate, so it might be very fast or it might be very slow. And we wanted to look for all those kind of things. We looked at thousands of different of the what we call chirp rates, or the changing signals. Anyway, we had a lot of computing time, so we looked at a lot of different kinds of signals. Anyway, so the best ones that we found are things that repeated on the sky over the 20 years. The telescope would occasionally come back to the same place in the sky. And if we saw it again at the same place in the sky at roughly the same frequency and the same kind of signal, if it repeated many times, that's what piqued our interest.
Now, those repeating signals, what came of them? Are any still a mystery, or were you able to eliminate all of them at some point?
Okay, so we first step was the SETI at home people they did the bulk of the computing, the volunteers on their home computers or desktops or in their offices or using their cell phones. They would analyze all the pieces of the sky. They would find kind of they made the first big data analysis. And we ended up with a list of about 25 billion different kinds of signals that we call them detections. We don't know what they were. And then we went through those 25 billion things and we looked at the ones that repeated, and we looked at how strong they were each time we saw them, how many times we could have seen them, how many times we did see them, and how close they were in space. Anyway, we had a whole bunch of different factors where the computer could rank them and score them. And it also, the computer there was a lot of work in trying to figure out about your question, were they really from ET? Or as you know, there's a big problem in SETI where you're looking for extraterrestrial signals, but what you find is terrestrial. We call it radio pollution or radio frequency interference. There's so many satellites and cell phones and Wi-Fi. There's all kinds of radio pollution, and we had to sort through all those 25 billion things and say what is caused by human activity, human technology here on our planet. And that problem, this radio pollution problem, is getting worse and worse. There are more and more transmitters and more cell phones and television and Wi-Fi, and it may be eventually humans will have to go to the backside of the moon. The moon would act like a big shield from all our radio pollution. We could put a big telescope there, but that would be really expensive. Anyway, so the computer, it took a few days to analyze the 25 billion signals, but we did that about 100 times because we kept optimizing every time we made a run on a big supercomputer in Germany at the Max Planck Institute. We would keep optimizing and retweaking and refining our algorithms to help get rid of the interference and do a better job of ranking and scoring. And the way we optimized, the way we kind of improved things was we injected a whole bunch of fake signals, fake extraterrestrial signals. We injected about 35,000 signals with different strengths and different kinds of signals, pulsing signals and drifting signals. Then we did the analysis on their supercomputer, and we found out how many of those did we actually see. And we said, oh, we're not seeing some of these. Why aren't we doing that? We kept changing our algorithms. And after about 2 years, we finally got to a really good place where we could find most of the signals that we had buried in there, the fake signals that we had buried in there. Anyway, so that's how we found the best candidates. Long story.
Are any of them still standing, or just we don't know? And are they being actively looked at again?
Yeah, so we're just starting to look at what we call the re-observations when we use the FAST telescope. And so far, and this is early days, none of them look interesting. We haven't confirmed any of the things that we saw at Arecibo. We keep them on our list, but actually we're just kind of getting started on the data analysis. And so I can't say right now that these 100 things that we've looked at are definitely not ET. So you're going to have to ask me another year or so.
Now, what about SETI at home, which is, I guess, currently on ice? Is that at some point going to be useful again to revamp and create a new SETI at home, or is it just in this age of AI and everything like that? It's just no longer. We don't live in those times anymore.
Yeah, it's interesting you asked that. So SETI at home, I think if you did it again, we could be even more powerful than the SETI at home search that we did. It's still the most sensitive search on the planet, but the weakness of SETI at home was, even though it looked at all these different kinds of signals and it was way more sensitive than anything that we or anybody's done, the weakness was we could not look at a broad range of the spectrum. We couldn't look at a broad range of radio frequencies. And so we had, actually at Arecibo, we had two instruments. We had the SERENDIP 6 instrument, which looked at a broad range of frequencies, every frequency the receiver could see, but it didn't do nearly as thorough a job. So it wasn't as sensitive. The instrument, the SERENDIP 6 instrument, was right at Arecibo, so it could handle a huge amount of data, but it couldn't do a very good job because it wasn't a big, powerful supercomputer like SETI at home. SETI at home could look at a kind of narrow range of frequencies, but it did it exquisitely well. And the reason that it could only look at a narrow range of frequencies, a narrow band of radio frequencies, was because we had to get the data out over the internet to the volunteers. There were 8 million volunteers in 200 countries. At the time we started the project, that people did not have very good connections to the internet. But now that's changed. A lot of people have fiber, really good internet connections, and we could analyze a much wider part of the radio spectrum. So the Chinese are actually interested in this, of running something like a SETI at home project on the FAST telescope. We're just talking to them now and exploring these different ideas, but it would be a great kind of project. We could do a much better job than the original SETI at home project, looking at a much wider band, but still have the even better sensitivity than we had at Arecibo.
Yeah, especially when you're doing surveys, the raster scan. It would seem to be, it might be useful to have that just to run weed through all of that data, which has got to be vast.
Yeah, we kept the petabytes of data from Arecibo, but I think that now with the more modern technology, we could record and send out much more data from the FAST telescope. Anyway, we're in the early days. We're just talking to them about it. And we've been talking about a new experiment, which they're building this kind of all sky, all the time kind of antenna. So these big antennas, they only look at about a millionth of the sky at a time. It has a very narrow beam, the FAST telescope or any big telescope. But we want to build something that can look at a big chunk of the sky all at once, like our PanoSETI experiment. And the reason you want to look at a big chunk of the sky is because maybe the signals are on maybe very rarely, like maybe there's a flash every month or something. And if you're pointing a telescope that only looks at a small patch of the sky, you might be looking at one place in the sky and the flash will be coming from another place of the sky. But if you can build some kind of gadget that looks at a lot of places in the sky, that's what we're doing with PanoSETI, looking for visible signals like a lighthouse kind of flash. We also want to do that in the radio. And China has some new technology that might be able to do that. And so we're talking to them about doing an experiment like that.
Well, it's an interesting thought to flip it around and wonder, okay, somebody 10 light years away looking at Earth, what are they likely to see? And the answer is not much. But that very powerful radar stuff that they were doing with the asteroids at Arecibo would have been, but the alien isn't going to see it unless they have PanoSETI, right?
Yeah, that's exactly right. So the Arecibo telescope was the most powerful transmitter ever on our planet. Not only was it a megawatt transmitter, but it was connected to the biggest telescope at the time on Earth. The FAST telescope does not have a transmitter, it only receives. Most radio telescopes only receive. The reason that Arecibo had a transmitter was that in astronomy, we just listen. We just listen to the waves coming from the universe. But there were other applications of Arecibo to study the atmosphere, where they would bounce signals. They would transmit signals up to the ionosphere. They would bounce back, and they could learn a lot about our atmosphere. And the other reason they had a transmitter was they were making maps of the planets and moons going around other planets and asteroids, and they would bounce signals off. It was a radar. They would bounce signals off these planets and asteroids and moons, and they could figure out what they were made of and make sort of maps of the surfaces of these asteroids. there's nothing that powerful on Earth anymore, as that transmitter on Arecibo could be detected on the other side of the galaxy, 10,000 light years away or even further. So it could reach 200 billion stars, that transmitter. Of course, it would take a long time. It would take 10,000 years to get a message to the other side of the galaxy, traveling at the speed of light. But that was an incredibly powerful thing, and it was used quite a bit. And if ET just happened to be in one of those narrow beams, they might receive the signal. But I think, as you point out in your question, it was a very narrow beam. So the chance that ET, if they're out there, would be listening at the right time when they happen to be in one of those beams, pretty small. So there are more transmitters on Earth that are not as powerful as the Arecibo transmitter, but they send out signals in all directions. Television transmitters do that, these mountaintop transmitters. They send it to people all around the transmitter, but they also transmit out into space. But a more powerful thing is the ballistic missile early warning radar systems. These are radars that the US has them, the Russians has them. I'm not sure what other countries have them, but they're looking for incoming missiles, and they're sweeping across the sky. And those things are not as powerful as Arecibo, but they are kind of omnidirectional. They're sweeping, illuminating all the stars and galaxies.
So the power of those, though, would there be, let's say, 10 light years away again? Would they see that? I mean, what kind of a telescope would they need? What size in order to detect that kind of a signal?
Right. So I'm not sure how long Earthlings have been sending those signals, but I would imagine during the whole Cold War, since the 60s maybe. So we've been sending the signals for 60 years maybe. And so they're out there 60 light years out. That's tens of thousands of stars that they've already reached. But as you pointed out, the signals get weaker and weaker. They keep going, but they get weaker and weaker, and they're harder to detect, and they need a bigger and bigger telescope as if they're farther away. By the way, the early TV shows like Ed Sullivan, I Love Lucy, have gone past many tens of thousands of stars, and The Simpsons have gone past a few thousand stars. So how big a telescope? Of course, it depends, like as you were saying in your question, how close they are. So the nearest star is 4 light years away. If they're on something that close, which I doubt life would be on, the very nearest star. But if they're on something that close, they could receive it with a pretty small kind of Earth-sized telescope.
So it's not that hard. It's possible that somebody's seen us. Of course, they haven't sent us a signal, or else I would imagine it'd be out here.
The other thing is that it's going to be very hard to find a civilization that's just invented radio like we have. So if you look at the kind of history of the Earth, 4.5 billion years, we've only known about radio waves for 100 years. That's a blink of an eye in the history of the Earth. If you compress the history of the Earth at 4.5 billion years into 24 hours, we've only known about radio waves and ways to communicate with ET for the last 2,000ths of a second. So if all of Earth's history was compressed into 24 hours. So the chance of finding ET in that little tiny, that they just discovered radio and they just built their first big telescope, Arecibo or FAST, it's pretty tiny. So it's much more likely that we'll find life either more primitive than we are, plants, trees, bacteria, or much more advanced than we are. Our civilization is going to be around our star is going to be around another couple of billion years, so we could last a long time. Some stars are twice as old as we are, 10 billion years. Many planets are 10 billion years old, twice as old. So you can imagine lots of advanced civilizations. So it's very unlikely to me that they would just have telescopes the size that we do. Either they're not going to have telescopes at all, or they're going to have huge telescopes, the size of their star or the size of their planet. But this just to kind of find them at just the right time when they've just discovered radio and just learning how to build telescopes, that would be kind of unusual.
But it's a good thing for us, because the chances of us seeing an alien civilization are very great if they are very long-lived. So you got a good chance. If you've got a civilization that's been out there detectable for 20 million years or something like that, you got a good chance of seeing that if it actually is there. Yeah. And we could probably infer that if we ever did get an unambiguous signal, we could probably infer that alien civilization has been around for a while.
I think there's sort of two likely scenarios finding life out there. So one is to find kind of simple life by looking at the atmosphere of an exoplanet, or we might find simple life on just in our own solar system, Enceladus, a moon going around Saturn, or Europa, a moon going around Jupiter. Those moons have liquid water. We could, maybe there's something swimming around down there. That might happen in our lifetimes. We find primitive life there, or we analyze the atmosphere of an exoplanet. We find that it has molecules in the atmosphere which tell us there's life on that planet. That would tell us there's primitive life. So that's one kind of scenario. I think that's a fairly likely scenario that might happen in the next few decades. And the other scenario might be this search for technosignatures, the SETI search, where you're looking for advanced life. They have to be at least as advanced as we are. The chance if we find them is they're going to be, millions or even billions of years ahead of us. In that case, we could learn a lot. We could get on the galactic internet. We could learn kind of, Phil Morrison called it the archaeology of the future. We'd learn what's in our future.
Which is probably the most useful thing, because if you see they're building, Dyson swarms or whatever, something like that, then it's possible and that you can do it.
There's hope for our planet. They somehow figured out how to stop killing each other and live together in peace. And so, finding advanced civilization would be kind of a nice, hopeful sign.
I think so as well. But that leads into my next question on where to look. So when you decide on SETI targets for a targeted SETI search, you tend to favor stars, right? But what if alien civilizations don't really have much use for stars, and that if you're going to hear them or see them, they're going to be using a black hole or something like that? They're going to be inhabiting some area that you might not think an alien civilization would be, but there it is. So do you take a look at targets that are, like a black hole, just to see if there's anything there?
Yeah, actually, we have a whole category of stuff called exotica, and we do look at some black holes. And I think your question is kind of spot on. There's a kind of anthropocentric thinking in SETI that they're going to be like us, they're going to use our technology, but that would be very bizarre, in my opinion. Like, if you think about the way we were thinking about how to do SETI 200 years ago, there were people that said, well, we should build some big fires, smoke signals, use mirrors to signal the Martians by shining sunlight in their faces, building big geometric structures, squares and triangles and so on. And they would see this kind of there were all kinds of ideas that were the best at the time. And now we kind of laugh at them. And what that means is that 200 years from now, people will be just laughing at what we're doing. And so I think this idea that we know exactly where to look and to think that they're going to be on a star and a planet just like ours is probably pretty naive. And it would surprise me if the life is going to be just like ours, and that it could be based on a very different chemistry. It could be, there are a lot of things that could be different about them. And they may have very advanced technology, like you were saying, and maybe they get kind of tired of just being kind of far away from their star where there's not much energy, and they might build, big Dyson spheres to swallow all the energy from the star, or maybe all the energy in their galaxy, or somehow energy, the black hole. I have no idea. So I think it's very useful to look at lots of different places. The sky survey to me is very interesting because you're not kind of being anthropocentric in your thinking. You're not saying they're going to be like us. You just look everywhere. Black holes, exotic objects, gamma ray bursters, and planets that are like ours and stars that are like ours as well. So I kind of favor the sky survey. And I also favor searches that all kinds of different signal types. And I like my idea of SETI is try to do something new every year, because we really don't know what to look for or where to point the telescope.
Now, let's expand on PanoSETI, another area that you're working with. Tell us about that concept and just lay it out for us.
Okay, so we've been thinking about this problem that ET might not have a signal that's on all the time. Maybe it's like a lighthouse that is flashing. That's a really good way that they could send a bright signal, but they don't have to use a lot of energy. If you make a bright flash, and then you don't flash it for a day or a week for another flash, you don't need a lot of energy. You need a lot of energy during that, thousandth of a second when you make that bright signal, and then you don't need much energy for the next week when it's off. So we're looking for these flashes. That might be an interesting kind of signal. Hey, how are you? We use them a lot on Earth. But the problem with that is that we don't know when to point our telescope at a particular place. So you might point your telescope in one place, but the flash is coming from a different place. And so in PanoSETI, we're trying to do what's called all sky all the time, or at least look at a big chunk of the sky all at once. And this is looking for not radio signals, but looking for signals in the visible part of the electromagnetic spectrum, the parts that you and I can see, the red, blue, green. We look a little bit in the infrared. That we can't see that with our eyes, but that's another part of the electromagnetic spectrum. And the way it works is we have a telescope that's it can look at a pretty big chunk of the sky, about 100 square degrees. So it looks at about a 10 degree by 10 degree chunk of the sky. But that's not the whole sky, obviously, but that's a very wide field telescope. And we hope that we have about 100 of those telescopes. We don't have this now, we have only 3 telescopes. But what we'd like to build is a thing with 100 telescopes, all pointing in different directions. So this telescope would look at this chunk of the sky, this other telescope would be pointing to a different, and what it looks like, it's kind of a dome with a bunch of telescopes poking out in different directions, kind of like a fly's eye looks. So we're learning how to do that. We've had a telescope at Lick Observatory. Well, we've had these 3 telescopes at Lick Observatory, where I just got back yesterday, where I've been for a week with my PanoSETI colleagues, looking for these flashes. We're just in the early days. And what's really exciting to me is most astronomers, they don't look for short time scale things. They don't look for things that are changing on short time scale. So most astronomers, almost all of them, they assume the universe is sort of pretty much stagnant. Things are changing over thousands of years or millions of years or billions of years time scale. So when they take a picture of the sky, they open the shutter for typically minutes at a time. And so if something's changing quickly on 1,000th of a second or 1,000,000th of a second, they won't notice that. They won't see a short flash. So maybe there are some flashes out there, but nobody would notice. So we're going to look at the sky. We're making a movie of the sky at 1 billion frames a second. So we can look for what's called nanosecond flashes. That's 1,000,000th of a second long. We can also look for 1,000,000th of a second, 1,000th of a second, a flash that's even 1 second long. We're looking at a lot of different time scales that are largely kind of unexplored. Nobody's looked at this kind of time scale at the universe at this kind of time scale. And the reason I'm excited about that is in astronomy and in nature, if you want to find something new and make a discovery, one way to do that is to just look at something that nobody's looked at before. You can look at a new kind of wavelength, look in the infrared or X-rays or gamma rays. The first time that people looked there was phenomena to be discovered. Or look at a new size scale, or in this case, we're looking at a new time scale. We don't understand why nature does that, why all time scales are populated. You can look anywhere and all different size scales. There's things at big, huge, galaxies, clusters, galaxies. There's things on little tiny time scales, smaller than an atom, at all different size scales. So we expect that by looking, and also the electromagnetic spectrum, there's stuff at gamma rays, X-rays, visible light, infrared, radio waves. No matter where you look, there's interesting phenomena. So by looking at this new time scale that nobody's looked at before, maybe we'll discover something interesting. Maybe not ET, but maybe some new astrophysical phenomena. So I'm excited about that. Anyway, we're just getting started. We're trying to raise money to build the 100 telescope thing. It's working pretty well. And one kind of really cool thing that's happened was that we had this problem with PanoSETI that we were looking from flashes from ET or something, maybe from a black hole or a gamma ray burst or something out in the universe. And we had this problem that there are flashes in the atmosphere. Turns out if a high energy particle, a gamma ray comes into our atmosphere, it can make a flash. And we had to build something to try to get rid of this. We were saying, well, we don't want these false alarms. It's kind of like that radio pollution. When you're looking for radio signals from ET, you find radio signals from terrestrials. This was kind of our form of pollution, this radiation from the gamma rays hitting the atmosphere and making a flash. So we tried to figure out how to get rid of that and not think, oh, we found ET when we really just found a flash in the atmosphere. Anyway, it turned out those gamma rays are what we thought was kind of annoying was somebody else's science. And there's this really interesting problem of people that are studying gamma rays, these super high energy gamma rays that are peta-electron volts or 100 peta-electron volts. They're much higher energy than anything that humans can make in the biggest super collider on Earth, the CERN super collider. And they're coming from space, but we don't know what's causing them. We don't know where they're coming from or what could make that huge energy, the 100 peta-electron volts. energy. And it turns out the SETI telescopes are ideal for trying to answer this question, where are these super high energy gamma rays coming from? So we're working with the gamma ray community to try to answer some of the questions that they've been thinking about. And then there was another application of SETI, which we hadn't anticipated. These people that are looking for dark matter. So this is a big problem in astronomy, is we know there's a lot of dark matter out there, and the galaxies are held together by dark matter, but we have no idea what the dark matter is made of. And there are some different ideas, but one idea is for a particular kind of new particle. Maybe we don't know what the name of it is, but some new kind of particle. And occasionally those particles would smash into each other, and that would cause gamma rays to come out. And we should be able to detect those with our SETI telescope. Anyway, this is it's a really cool spin-off of SETIs. We might be able to shed light on this question: what is the dark matter made of?
Is that like a recent interview I did was on the Amaterasu particle, cosmic ray? And is that the same sort of phenomenon?
Yeah, in fact, we're working with the people that run the Veritas project, and we brought our telescopes up to the Veritas mountain, and we kind of observed with their telescope and our telescope simultaneously. And it turns out, if you want to look for these ultra high energy events, they have a really big telescope. If you want to look for these really powerful gamma rays, you don't need a big telescope like Veritas. What you want is a lot of little telescopes that are much cheaper than the Veritas telescope. And so this thing that we're building with 100 telescopes is actually a lot better. You can kind of parcel them out, and then you can have a much better chance with detect. So the gamma rays, these high energy ones, are super bright. You don't need a big telescope, but what you want is a lot of different telescopes because they're very rare. So if you just have one telescope, it's going to be really hard to find them. But if you have a lot of telescopes, you can track them down.
That's interesting. So this approach for SETI is not just limited to SETI, but everything, or at least a lot of other things can benefit from the same technique. Now, working with the scientists in China on SETI, do they have a different take? Do they have a different sort of idea on how SETI should be done? Or are they basically the same as far as their thinking as Western astronomers are?
I think China is kind of new in SETI. So they're doing really good SETI experiments, but they're only a few years old. And so they are not trying to do something radically different, because I think part of it's my fault. They learned about SETI from me and other Westerners. And so I would say that they're doing a better job because they have bigger telescopes, and they do have good ideas, and they have a lot of smart people. Their students and the researchers there are really interesting to work with. So far, the SETI that they've been doing is using the same ideas that have been developed in the West, but kind of optimistic in the long run that now that they've kind of gotten up to speed on kind of the Western kind of traditional SETI, they've already got some interesting ideas. I mentioned that they're thinking about this all sky all the time in the radio, which is a very complicated thing to do. Look for these rare things, but in the radio, SETI does it the visible, so that'd be exciting. Anyway, so they've got some creative ideas, and they've already got the best telescope to do SETI, and now they've been at it a few years, and they're sort of catching up to the people that, like me, that have been doing it for 50 years, and maybe they'll get better at it. I think they will. But it's interesting, your question, I want to kind of twist it around a little bit. So in the early days of SETI, the 60s and the 70s, there were different groups developing different ideas. So the Russians were kind of isolated from the West, and they had some very different they were just as creative as the Westerners, and they had some very different ideas about what to look for. And I think that kind of isolation from the West is kind of interesting about how they were looking for these pulses. They did really interesting experiments. And I think that were very different from what we thought their ideas were just as good as the West, maybe even better, but we had our kind of orthodoxy and they had their orthodoxy. And it was kind of healthy to not communicate. Maybe the Cold War was useful, because I think once you start communicating with each other, you kind of converge and you do the same experiments.
That actually happened during the Soviet era, the Cold War. That actually happened with a number of areas of science. For example, metallurgy. And it turns out the Soviets were much more advanced on metallurgy than the West was in a lot of ways.
Yeah.
And they still, to this day, all the new elements that are created in the accelerators It's usually done by Russia, Russian scientists.
The Russians had some amazing people in astronomy, the cosmology, that in many ways was far ahead of the Western stuff. They had a lot of great ideas. And we had, in the early days, we had a guy named Alex Zalay, who's now a professor in Baltimore at Johns Hopkins. But when he came to Berkeley, he was a postdoc, and he had worked closely with the Russians. And we just learned about all this amazing stuff that Alex brought with him when he had spent a little, he's Hungarian, but he had spent some time working with the Russian cosmologists. And they were doing a lot of stuff that we had never thought of.
Yeah, that's my hope with China in all areas of science, is that they might have a different bent on it, and a different sort of a fresh way of thinking that might benefit everybody, especially since they're only just now getting into a lot of fields.
Yeah, I think I'm hoping you're right, but unfortunately, you might be wrong, because I think there's so much influence in both directions, because the internet, it's easy for us to read what they're doing and them to read what we're doing. There's a lot of wonderful communication going on. So I think there's maybe too much convergence, not enough wild and crazy ideas.
All right, Doctor, thank you for joining us today. And I look forward to further research and the developments with FAST, because I think that telescope is, number one, innovative. And if you can apply it to SETI this way, with openness from China to actually do that, then it's going to just make everything much, much more easier to do in the future as far as SETI goes.
Yeah, I hope you're right. I'm excited I think that Earthlings are just getting in the game, but I'm optimistic in the long run. If you look at how far we've come since the early days of SETI, we used to listen to one channel at a time. Now we listen to 100 billions of channels. Now we got these big telescopes. And if that trend keeps going, that exponential growth, I think right now we'd be very lucky to find these signals if they're out there. But eventually, maybe in our lifetimes, or maybe our students or our students' Earthlings are going to be able to answer this question, are we alone?
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.